Log on, tune in, find out. Another good idea from Cambridge.
Weng-Kee Wong on nature-inspired metaheuristic algorithms for generating optimal experimental designs, something we heard briefly about last Wednesday morning at the session on numerical methods and optimization.
Thank you. Thank you, Steve Gilmore, for inviting me, and also to the organizers for putting this marvelous conference. There's a lot of ground to cover, so I'll just go right into it, and I hope I will be able to actually demonstrate what this does in real time for you. I have collaborators, and they are mainly from Taiwan, and I'm not sure I will have a chance to talk about this work with someone in Portugal that I don't really know who this person is, whether he or she, or whether it's a 20-year-old or 50, 80-year-old person. I don't know, but it's very nice every time. They're from engineering department. I'll show you that a couple of my papers on Minimax have drawn a lot of attention from people, particularly in the Middle East and engineering. So here's the last one, and in this case, we do have actually quite good traction and have things going on. I'll tell you a bit about what motivates me recently, and this is coming from an applied person looking at optimal design theory. So have that in your mind, and then there's the outline you'll see. So from the experience with this field, it's really quite mathematical and challenging. Not many people can do the mathematics like what you have just seen. The formulas are very complicated. You just can't remember it the moment you put it away. And you look at the formula, it's always quite curious. They always have some restrictions, some assumptions that are not made clear. And for the practitioners, I would think they find it inadequate for their applications. So how can we do a better job in communicating and telling them that, you know, we can do really some exciting things and in a way that make them interested. So you might think algorithms is probably one of the ways. You just let it run, and then as Doug Montgomery, if he's here, people are impatient. They just want to get results quickly. They can spend a lot of time waiting for you to derive the theorem, and in many cases, it's not doable. So here's one typical example. Logistic regression on -1 to 1, and you say, let's find the locally optimal design. And well, typically it goes like this, and after that, essentially what it means is you partition the parameter space cleverly, and you'll come up with results like, depending how theta 1, theta 2 is related, you have sometimes, in this case, 2-point design, sometimes supported at the extreme points and not. You all must have seen this result before, and if I get 80% of the people would know at least where is this taken from. Did anybody verify this result before? It's interesting. I'll come back to this in a bit. Now, you look at this example, which I claim is typical. That's one result, and it just stays there by itself. And the practitioners look at it, well, my design space is -1 to 1, so you could have, say, log dosage, and you work with that interval. And what happens if my dosage interval is -2 to 2 or something else? It's not really clear from what you can deduce from the previous results. And sometimes it can be just plain wrong to just say, well, I just multiply 2 to the support points for the first place and get the result I want on -2 and 2. I don't really want to estimate 2 parameters. I just want to estimate one of them. How do I do it? Well, not clear. I am interested primarily in theta 2, the slope, and can I design for that? So these are practical questions that people may want to know, and the result just doesn't quite do it by itself. Other questions you see, I want a 3-point design, where the extra point should be, and how good is the popular 3-point design. So all this, I think many of us know the answers, and so why not make it more accessible? So here's another result. You'll see, I forget who the author is, but I think you can guess very well who the author is. So these are typical results you see in optimal design theory. And it's actually very fascinating if you care to go through it. This is polynomial regression. And now you allow for heteroscedasticity. So lambda x is the reciprocal of the variance, and it tells you that look at those functions. UV is confined to either 0 or 1, and then and go on. And probably it's one of those things I always experience. Am I going to solve this? Well, probably not. And is there a better way? Well, you can say I can program this and so that it's available to me, but that's not what is happening. But I'm going to tell you, I think there's a way that, well, look at this. UV is 0 and 1. What happened? I want 2. Well, you would imagine that the mathematics would just collapse and doesn't give you any hint what that is. So I think I have a way of actually finding the design. You give me any UV, or for that any matter, anything, and I can generate a design faster than you read this theorem. Okay, let alone understand the theorem. So you probably take for you, quite a while to understand what this is, but never mind that. So I have, with some help, think that a website is clearly a way to go to make optimal designs more accessible. And you consolidate results, scatter over the literature. I find optimal designs published in Journal of Marine Science, Australian, New Zealand Mathematics, and I spent quite a few days working on it only to discover people have done it, so that's very frustrating. So it's a good idea to consolidate and put things together, and you can generate designs that are tailor-made. So if you want logistic and I only want one parameter, well, there's a way to do that. And why not incorporate the results so that people just go and, with a few strokes, get the design you want. And you can study properties very much easier and just make your life a lot easier when the results are available. So there's a website there that, with the help of a couple of people here, is going. It's by no means perfect. It's just an attempt to get this thing going. And one of my points here is hopefully there will be a collective effort to get this thing a lot better. So there's some demonstration there. I'm not going to have time to demonstrate on this website, but you can visit it and play around with it. So having got this website, the next question is, well, where do you go from here? I'm convinced it's a very useful piece of research for educational purposes to get students interested in. However, it's very time consuming. Labor intensive to do all this stuff, and of course little reward. You can spend time writing paper, grants, and it's costly. And you would need to work with a lot of people with different expertise, programming, and people very good in optimal design theories. You look at the papers, sometimes you can do case 1, case 2, but not case 3, and then you leave a gap there, right? So you need to fill in the harder part of the theory to complete the solutions. And then more interestingly, well, how many models and criteria are you going to put on the website? So on the list now, there are several, but then there are always some people looking for something else. So is there a way to actually make it cover any models, any criteria? Okay. So are there ways to even make it more accessible and exciting? And the answer is yes, I think there is a way for doing that. And we have to do something different than what we have been doing. And my relationship with this meta-heuristic stuff is only a couple of months old. And I hope it has been very positive so far. So I'm excited to share with you what I have discovered. I gave a talk, I think, beginning of June in the Discrete Math Conference in Canada. And at that time, I don't have actually a lot of concrete results to show, and I'll show you some of the things that we have developed in the last couple of months. So meta-heuristic, I didn't know that. Actually, it's a recognized field in computer science, right? And what it does essentially, well, it's like finding solutions, optimizing something. And the brown stuff says, well, we make no assumptions about the problems, which is very interesting. You just search, and somehow these heuristics will get you close to what you want and perhaps optimal without actually guaranteeing you that you have an optimal solution. Well, and then it's stochastic. We want things to be random. So the interest here is nature inspired, and I'm going to focus on PSO. And it's a method that I don't think has been filtered into mainstream statistics yet. So this is something I steal from the internet, has some quite nice picture, And PSO typically associated with flocks of birds or fish, right? And why is this interesting? Well, here's a brief history. It started in '95, somebody proposed it. And then after that, almost every year, IEEE would sponsor at least one of this, not just one. And there are tons and tons of tutorials, right? If you just happen to, by chance, Google PSO, you'll be stunned. There are tutorials, codes for you to download and implement and use. And there are so many applications that people have to keep track of it. YouTube is not just for video and for your listening pleasure. There are hundreds of postings that you can see, and people tell you what those things are. There are monographs, and even a journal was born in 2007 just to keep track of what this stuff is going. And there's a conference in France just this June, and notice the word theoretical advances. So while it seems like there's heuristics, but apparently it's working so well that people are very interested to understand what the heck is going on. And there's a book published by the original proposers in 2001, and it has been sold out 3 times. And another person here, you see here's a book, 2008, and the second edition is 2010. And this is a senior researcher at Cambridge University. So I was so excited to come and maybe say hello to him. But he has moved to Oxford. And the second edition has 50 more pages than the first to just simply update, to basically tell us how exciting and how fast things are moving. I don't see this in statistics. So what is it about? So you can see in the Paris talk, or in France, these are some of the talks title that basically tells you what PSO could do. And I look at this and I say, wow, that seems very impressive. And I think we can do something with, try to apply this to optimal design and see what it does. So my job here is to convince you PSO actually is quite awesome. So how do I convince you? I know there are already skeptics in the audience. So if I find the optimal design, oh wow, you would say it's quite easy. That's the simplest type of design. So I'm not convinced. I could do something else, see optimality and other stuff, but may not be persuasive enough. So what should I do? Well, I go back and work with what I think is some problem notoriously difficult and alluded to by Douglas Montgomery, minimax design. So these are very difficult problems because you're not just minimizing one thing, but actually 2 or 3 layers going on. And what can I do? So I look at the literature and see all those published results on minimax design, and I'm going to use the PSO method, generate it, and compare the designs, right? And with the assumption that if it works for such a complicated problem, minimax, it should really work well for de-optimality and other stuff. So I'm going to give you a couple of examples, and this session is on nonlinear models, so I have something on nonlinear models as well. So minimax arises in many contexts. You could say I want to minimize the maximum variance of the estimated parameters in the model, right? You could be interested in extrapolation, and this is usually the typical motivation. In dose response studies, say you have a linear model or whatever model you may have, and for safety reasons, it's confined to a certain interval, but doesn't stop you from making inference what goes on if you give at a higher dose. So you like to model the response, and you might say I have so many doses that I want to explore outside the safety limits, and maybe I should try to design a study that minimizes the maximum variances across the extrapolated doses. And 2 weeks ago, or 3 weeks ago, we have a healthcare program workshop, and many speakers allude to the maximum tolerated dose. Let's design to estimate that. And I hear many of them will say, but it's also very good to know what is going on around it, right? So this is actually not for extrapolation. You can be doing interpolation as well. So you could have an objective, let's estimate MTD, subject to I have 90% efficiency for estimating MTD. I want to do well also in estimating in the neighborhood of the MTD. So that can be done. So the founders of optimal design has actually worked on this area quite extensively. And they assume you have a polynomial model, homoscedastic constant variance. and the prototype interval minus 1, 1, and then again for different values of a, b, they were able to actually calculate some analytic results. So a equals to minus 1 and a equals to 1, they're able to get some results. But for arbitrary results, intervals z is not available. So this reminds us of minimax e-optimality. E-optimal designs over the last 2 decades, people were cranking out results. The result apply only for this type of interval, and then people extend to different types of intervals. And now we have the solution, and we can actually all put that on the website. So here's just a rough theory. Why is this problem so difficult? So let's look at a polynomial regression model, standard polynomial efficiency function inversely proportional to the variance. And what you want to do is to minimize the variance at the point x. So that's the variance you see here. And if it's just one point, I know what to do. But if there are several points, what I can do is, well, z contains all the doses of interest, and I try to minimize the maximum variances across the interval z. It doesn't have to be interval. It can be any compact set so that your design exists. Now this is convex, right? This function is still convex, and so the equivalence theorem still apply, except that it looks quite ugly. And there are a couple of versions, but this is a version that I think Anthony Atkinson and Vera Fedorov has, and many authors allude to it. They have it there. And over the years, not many people actually pick up and work on it. So what this says is this. Equivalence theorem basically says if you are so lucky as to guess the design correctly, and then make sure this is satisfied, right? So there's a mu star there that complicates things a lot. So first of all, you have to find all those points that maximize the variance, and then put a probability measure on this set so that this thing happens. So the trick is, if you guess correctly, but you find this measure wrongly or fail to find it, then you cannot verify the design as well. So I don't actually see a lot of proof easily, so I squeezed in the proof in one of these papers for those who are interested. You can read it using a risk representation theorem in functional analysis. You can arrive at that. Other details here. Now, mu star actually can be shown to be a maximum measure. So you are actually have another maximum problem going on here to find mu star correctly. And being convex, you can actually create a lower bound for any design. So here are some of the references that I refer to. So for the PSO, I'm not going to spend a lot of time on this. Just Google, you'll see tons of stuff there. These are the two key equations in this method. And what is so different from this method, like what we are most familiar with, Fedorov-Wien algorithm? The algorithm starts from one point, right, and then it just goes around and picks and finally converges. It takes a long time. But here I say, well, why start with 1? Start with 100, 200, whatever you want, and let every bird find the optimal place, the food, right? And then we share information at the same time. So here you have, this is where the bird is at this time. This is the local best the bird has, and this is the global best. And somehow these two very simple equations, and their tuning constants that need not concern us, you can actually find the design. So it's a bit mysterious, but it seems it works very well for those problems you've seen, and in optimal design. So what I have here is, it looks like we have a generic algorithm, and I believe you can just download this algorithm from the internet or somewhere else, and simply change the information matrix and the criterion and let it run, okay? Well, at least this is what my co-authors tell me, but they have PhD in optimization and differential equations, so they say it's easy to do so. And all you have to do here in the examples to follow, how large the flock of the bird is, whether 200 birds or 500 birds, how many support points those design have initially, and number of iterations. So here's one example. I have a cubic regression, and here's the efficiency function. I run the PSO. I get these two designs on two cases. And you can compute the efficiency lower bound, and it takes just seconds to generate the plot. So what you don't want to see is you have this thing going up here. So anything that crosses the 0 suggests it's not optimal. So very quickly you can verify that, oh, well, it seems it works. So here you try to minimax single parameters. So you want to minimize the maximum parameters from 2 estimated variances. And you can do this. It takes about 5-6 pages of calculation. And there's some key constant, and it shows that it's either 2 or 3 support, depending the nominal values. And here are just 3 cases that we look at. You find that again the results coincide with those published in the literature, except for this one. But all this means is that we have not run enough iteration. If we run a few more iterations, you'll get exactly what you want. And again, all this just takes a couple of seconds of CPU time. This is logistic. So now I'm saying, let's try to minimize the maximum inefficiency of the estimates. So instead of locally optimal, I think that A belongs to some interval AB. So some interval 0 and 0.25, and B belongs to this interval. How do I design to make sure that no matter what the true value is, I don't get too bad? So you just run this so there are 2 optimizations going on here. So this is for mu star, and this is for the optimum design. You can play around with this, and you get this thing very quickly. I remember when I did this in 2000, what I did was, if you make a bad guess, all these things is very hard to guess on the structure of the design. And if you guess wrong, then good luck to you. You can just work with the equivalence theorem and never get it. It took, what I did was I ran Federal algorithm a while. It never converged, but give me a clue how many support points it needs. Then I'll switch on to Mathematica, and then numerically try to calculate it. And sometimes it was successful, and sometimes it's not. So look and behold, now this method actually gives you the design in just a few seconds. So last example, Michaelis-Menten model is the simplest biological models, equivalent to the simple linear regression in my mind. And you can use Efling theorem and complicated theory to arrive at this result. And so this was done a while back. So that's the theoretical optimal design, and this is what's generated by the PSO. What is interesting here, these 2 don't agree. And what we did was, well, we used more iterations, more runs, and it still didn't agree. So eventually, we actually went back and checked and used the formula, and this was actually calculated incorrectly.
You did that.
Yes, this is a paper. So here a little bit. You see, in the second iteration, I don't know.
I mean, it's 6 instead of a 5 or something.
I don't know, but there are more printing errors that you can discover so easily, because now all you do is just let it run, and you don't want to calculate. So a little bit more details here. This is finding the minimum of the largest eigenvalue. Literally in the second iteration, the PSO managed to zoom on that, and you will see, well, you start with whatever points you have. That's the starting one, and essentially just sparkles, and then go there, and then go there, and boom, that's the one. So all this can be shown in a few minutes. So this is what I say. This result actually is incorrect. Can you believe that? We ran this because now it's so easy to run, and we just run many test cases, and that's why we did not get the results that is claimed here. And it's a very sobering thought, because every time I teach optimal design, which is about once every 2 years at UCLA, I always tell the student, verify this result. If you have problems, come and tell me, and none of them ever did in the last 20 years. So what's wrong with this? Actually, what transpired, you just have to interchange these 2 things. So case 2 and case 3, the results are just typo. So that's the typo I alluded to. So it's very easy and convenient to do all these things. I just have to squeeze in these 2 slides and say that please think about using multiple objective designs, because I think they're really not that difficult to just calculate a D or something. So these are things like this. You have models. Some parameters are more interesting than others. You have concern about model inadequacy, so you want to do this. So all this can be done quite straightforwardly, and you can just refer to some of this paper where there are examples how to actually construct a multiple objective designs. So I think I will not have time to do the demonstrations, but I'm happy to if there are people who wants to see it. So what I'm suggesting here is, as people noted, it's very simple, efficient, so mysterious and yet powerful. And what I suggest is, so now you give me any model, I'll be interested to actually experiment, run on it, change the criteria, supply the information matrix, and if you don't have faith in the results, you can still use the equivalence theorem. But otherwise, just change the parameters if it doesn't converge, and then let those sparkling do the work for you, right? And then you get the designs. And remember, this thing doesn't require the convexity or differentiability, which is not surprising. You remember the first application on stock market indices. Well, it would be wonderful if that thing is convex, but it's not, right? So this thing is much more powerful. It can be applied to many other things, like including fMRI, right? You have multiple globe and all these things. I think there's more to it. People working on adaptive designs. They are adaptive PSO algorithms. So there are lots to be exact optimal design. So can this thing actually generate all that? So there are lots of things to actually discover. So lest you think there's only one thing out there, these are so many other things that other people are working on with very nice name and interesting properties. Have you heard of this? Well, somebody there, I was so excited to realize that somebody is going to talk about ant colony, I think this Friday. So I think we are really shortchanging ourselves if we just stick to the optimal design group and using the same traditional theory and not try to incorporate what goes on in the outside world and just look at how many things. Why is this in red? This thing is in red. This is the same guy. Well, he actually claimed this cuckoo search outbids the PSO methods. Right? So they have all these test function and preliminary results, and as what he claimed here, actually this thing outperformed the PSO method. Okay, so in summary, I demonstrate to you the alternative methods that we really should consider incorporating in optimal design literature. I think it's actually a leap forward to be able to find all these optimal designs very easily when mathematics fail, and then you can use the equivalence theorem to do that. So this guy from Portugal has been actually solving a lot of interesting problems for me, including back to the logistic minimax design, where the two parameters are only allowed to vary between two independent intervals. Now you could think that, well, the range of the slope depends on the range of the intercept. So he was able to actually generate using semi-infinite programming, which essentially means infinitely constrained. Well, that seems very strange to us, but there's such thing. You can optimize some function with infinitely many constraints. Anyhow, I hope that there will be a collective effort to promote optimal design, and thank you.
Time for a couple of questions, although I presume lots of you will want to swarm round Weng-Kee with debating points.
So I apologize, I didn't have time to actually show you all the sparkling, and then it generates the equivalence plot, but I hope you are excited about this possibility.
Any questions?
So I just comment that it's the design analogy to Winbugs.
Oh, yeah.
But I think it's very exciting. I mean, it takes so much time to find optimal design, so laborious, and now it looks like for all the examples that we've looked through so, it just generates the optimal design.
Well, one question. You seem exercised about changing the design interval,
Yeah.
but for some models, standardized design variables have been established, optimal design is found for them, and then you can linearly transform back to other design intervals.
Well, some you can do and some you can't.
Yeah.
But all I'm saying is there are a lot of theory that goes into it. But then we can put this at the back, of the website, but for practitioners, you need just a website to allow them to change things and see what's the optimal design. Yeah.
Okay, one more.
You mentioned tuning parameters.
Yes.
Were the tuning parameters chosen using knowledge from optimum designs which people already know?
Well, the truth is, if you look at the PSO literature, they would say 16 birds or 10 or 15 iteration is normally will work. So what you see here, you can use 100. You can study the impact of different choices of the iteration. There are actually 2 iteration numbers and 2 flops because there are 2 optimization going on here. But the truth is, it generates the design so quickly that it doesn't really matter what you start off with. And you can see whether it converges or not, because when the result shows up, and all these are programmed in MATLAB code, you see that the last few iterations, the results still don't agree to the 3rd or 4th decimal places, then you probably need more iteration. So, but since it's so cheap and easy, it doesn't cost anything. So
Okay, I think we best move on. Thanks again to Weng-Kee.